My name is Pierce Giffin, and I'm a graduate student at the University of California, Santa Cruz in the Department of Physics. My research is in the field of theoretical astroparticle physics, where researchers like myself are determined to understand the true nature of particle dark matter. Over the past 50 years, scientists have found evidence for the existence of dark matter on large astrophysical scales. This new exotic type of matter is believed to exist in and around most galaxies, including our own. Observations of galaxy rotation curves, gravitational lensing, and the cosmic microwave background show that types of matter we currently understand are not enough to explain the natural phenomena of the universe. They provide evidence instead for the existence of a new type of matter, primarily through its gravitational interactions. As of now, we still know very little about dark matter. We know that we can't see it and it doesn't interact very strongly with electromagnetic forces, hence the name dark. We also know that it's a pretty rare interaction for dark matter particles to interact with another single particle of dark matter or of ordinary matter. We also know that there's a lot of it out there. In fact, we believe it outweighs the amount of ordinary matter in our universe by about a factor of 5, accounting for 26% of the total energy in the universe today. However, we have yet to really answer the question, what does a particle of dark matter look like? What is the mass of a dark matter particle? Does it behave like an electron, or more like the quarks that make up the nuclei of atoms? Or perhaps something new entirely? Are there any new underlying symmetries in our universe that a dark matter particle could help explain? These are the questions that theoretical physicists like myself are trying to answer. Through laboratory experiments, astrophysical observations, dark matter detectors, and sophisticated simulations, researchers have been working on all fronts to search for hints of the true particle nature of dark matter. What nearly all existing searches for dark matter have in common is the assumption that effects of dark matter can be observed from interactions of a single dark matter particle with either another dark matter particle or a particle of ordinary matter. My research expands the types of interactions we can search for by considering collective effects, or interactions that rely heavily on many particles working together to create an observable interaction. This idea is motivated by ordinary matter, which we already know how to describe at a particle level. In our universe, 99.9% of ordinary matter exists in the state known as a plasma. We can often think of plasmas as very hot gases, but a key difference is that their behavior is governed by collective effects rather than by the interactions between individual particles. If dark matter can produce these collective effects, then we can use many techniques from plasma physics to also learn about the particle nature of dark matter. One of the best places that we can look for dark matter is on extremely large scales, such as galaxy clusters. Shown here is the Bullet cluster, where a few billion years ago, these two clusters of galaxies began colliding with one another. We see in pink the X-ray emissions from all the regular matter plasmas that experience a large-scale collision mediated by collective plasma effects. This collision caused the ordinary matter to bunch up at the collision site, whereas the collision-less galaxies passed through each other completely unscathed. However, the dark matter shown in purple also did not experience any collisions, and we similarly see through gravitational lensing that the dark matter halos also pass through each other without any interruption or interaction. By modeling dark matter with these collective effects similar to those regular model plasmas, we can probe interactions much weaker than single particle interaction scenarios. Using our local high-performance computer LUX, we ran detailed simulations of the dark matter in the Bullet cluster system with these collective effects, concluding that dark matter interactions would produce unphysical results for couplings more than 10 orders of magnitude below what could be probed by previous studies. And in this work, we use this to show that dark matter is not something that can exhibit these collective effects, or we shouldn't be searching these for our laboratory experiments. I'd like to thank very much the ARCS Foundation, as well as both of my research advisors, Stefania Gori and Stefano Profumo, for the opportunity to perform this research. And for more information, be sure to check out my poster at the ARCS Symposium.